Uh, is it started? Not yet, right?
Recording has started.
Oh, it has started?
Yeah.
Okay, so I think it started. So, yeah, welcome back again to the tutorial session. Today we will discuss some questions regarding to line integrals. And let me share my screen now. Yeah, I hope this is clear. This is visible, sorry. Yeah, so here is the first question. So here we want to know the difference between the scalar field and the vector field. Uh, so can you quickly recall what is the difference between a scalar field and the vector field? Please give me a minute. I'll come back. So till then you see what is it. I'll just come.
Every point in a given space or something like that, like an electric field or something.
Sorry, can you repeat once again? So I did not hear it properly.
A field is something which assigns a value to
Mm-hmm.
the space. Like for example,
Right.
we have an electric field. Now, in a scalar
Okay.
field, the value of
Mm-hmm.
the output at each point will have only one output. Basically, it will be in R1, while for a vector field,
Wow.
the output will be in R something greater than 1.
Okay. But will that be vector field? Do we call it a vector field? Scalar field is okay that the element should map to R. It should be a scalar quantity. That would mean that it should not be a vector, meaning it should be one real number, right? So, yeah, so any function you define from any space Rn to R will be considered as a scalar field. That's okay. But what about vector field? I do not see any Rn to Rn by saying that it will be a vector field. Okay, so let me write what that is. So I think scalar field, as you said, scalar field is the one where you have f from any Rn to R, where it can be anything and greater than or equals to 1. We don't mind is even if it is from R to 1. So this is kind of the scalar field because this is a scalar quantity. Number itself, the name itself suggests what to say. But vector field, we do not call any map to vector field. But when it comes to this, then M should be N. You remember?
Yeah, yeah.
So the domain and codomain should have the same dimension. Then only we say the map is nothing but a vector field. As long as their dimensions are same, we can say. Otherwise, it's just a map. So this is a vector field. Okay. I just want to know that there is a difference between two such fields, and we will see this notion. All right. So here is another question. We have this graph which I have drawn in the xyz plane where I have one function. Now, if somebody asks you that we have this integral fxy ds over the curve c, Suppose I give you a curve also. Let me just draw the curve. I have not drawn the curve. Just a moment. I will simply change this axis by this axis. And here I'll draw. This is certain, let's say, to me, this is the curve C. Just a moment. Yeah, so what is basically, what do we say about this fxy dx? Does it depicts anything geometrically? Does it mean anything geometrically?
So this is the representation of the line integral. That is,
Yeah,
we will be summing up the values along the curve represented by the function fxy in
yeah,
the
this is
given domain.
right. What you say is exactly the meaning of integral, but does it have any geometric meaning? It's a meaning of what I'm writing. It's just the I'm finding the integral along the curve C of the function f, but does it have any meaning to this finding this integral? Another thing, uh, I can write this curve in many ways, right? If I can parameterize the curve C in many ways, I can parameterize in a several ways, whatever way I want it. Integral can be computed as long as I can parameterize, or I can have the same curve. The meaning is the same. I will just find the integral with respect to one parameterization. I will find the integral with respect to other parameterization. Does it have any relation? Those two things have any relation? It should have. So these are the natural question I
Repeat the
think I'm.
last thing which you mentioned.
Yeah, I asked that if suppose you have a curve and you want to parameterize the curve because you do not seem to convince yourself by just by looking at the curve what is the meaning of the curve. But once you parameterize it, maybe you have certain meaning to it. You can see the curve. So suppose you parameterize the curve in two different ways, and you want to integrate the function again on the since the curve is same, I can integrate the curve with respect to first parameterization, as well as I can find the integration over the second parameterization. Are they related? As long as the curve is same, the meaning is same.
Yeah,
So yeah, so such questions are most natural question one can ask, because if you are doing a choice based question, choice based means you have a choice to parameterize the curve. Once you have a choice, the natural question is that it should not depend on the choice you are making, right? So, and there should be a meaning. Once you are doing anything, there should be a meaning. Just like we saw, double integration would mean the area under the curve. The triple integration would mean the area where volume under the surface. Line integral should also have a meaning. Otherwise, why would anybody do it? Right? So the value is nothing but this is the area above the curve. If you have a curve and you are just below the sheet, below the surface, whatever you have, below the surface above the curve, there is a area, and this is what you are trying to compute, isn't it? I mean, if I just
yeah.
put the in a similar way that just we did in the double integration, I think if you remember, I did it something like this: 0 to f, and then certain limit of x, and I wrote it in this way: f dx and limits of x. And I said this is nothing but the area under F. The same thing here, but it has to be bounded by the curve. You are just integrating in the region which is just bounded by the curve. I mean, it you should not find the area below the curve, below the function. Um, Not everywhere you want to find the area. It has to be given that you should be remain inside the part which is defined by the curve. As long as you are covering the curve, you are finding this area, but as long as you are going beyond, you are actually not computing this thing. So it is nothing but, so geometrically it is the area under the I should say under the curve, sorry, under the surface fxy, or the sheet, whatever I'm saying here, fxy above the, I mean along the curve. I hope this has some meaning, like it says something at least, that this is not just any integral, but it has a meaning behind it. And the other question was that if I parameterize it, so if I ask you, just your guess, if I ask you that I parameterize in several ways, and finding the area by one parameterization and finding this area by another parameterization, uh, do they have any relation? Are they same or are they different or what?
As long as the surface is the same, they
Yeah,
should
everything.
be the
The
same.
surface is same, the curve is same. So what do you say? Yeah, this should be same. This is what. So we will see sometime later that it will not depend on the parameterization. Okay. So we will see. We'll see soon. Now here is the question. Find the value of this integral where c is the curve parameterized by these parameters. Can you compute it? What is that? Here, what is ds, by the way?
ds is the unit path that we are taking.
ds is the, d is always shows you there is a small change, right?
Yeah.
And when you are you have ds, then it's a small area or small volume or small length or some small change, but where you are looking, it depends. Here, what is this? Is it a small change of area or a small change of length or the volume or what?
Again, this context, it would be the very small change in area.
Yeah, so as you said, it is just a small change of area. Then, what is the meaning in this case? It would be,
So x plus y represents the curve or the plane, the area
mhm,
which we want to find, and ds is a very small change in that area.
right, right.
So using it,
So,
we are integrating all over the area.
right. So, as you understood this, when you have, okay, just let me recall. So, before writing any solution, I'll just recall. Suppose you have any f dx and you have ds, and you want to integrate over a curve. It's a line integral, as you said. And here in this case, you have a parameterization. So you have written x as a, let's say, it's a function of, I should say f, or if I have written, maybe I'll write x is as a function of t, y is a function of t, z is a function of t. All right. So here, when I write ds, what is the meaning. Can while we change this part in terms of t, it should also be changed in terms of t. Is there any way to do that? Because we are parameterizing the function, if suppose we are sorry parameterizing the curve, then function is going to change. It's going to change in that parameter which we are fixing, and therefore the change is also going to be in terms of that parameter, right? So here, if you remember the function that I'm writing here, can you tell me, is it a vector valued or scalar valued? It's a scalar field or vector field, the f?
F is a scalar field.
Yeah, it's a scalar field. If you remember, then for scalar field, this is nothing but the norm of, let's say, r prime t. I'll tell you what is r prime t dt, where your r is nothing but xt, yt, zt. And in this case, it is just xy, just these many. So, therefore, your r prime t will be nothing but x prime t, y prime t. So it depends what kind of function you have. As long as we have a scalar vector field, sorry, scalar field, if you remember, then we can do this thing. That ds can be written as this, and of course your f can be written in f of rt. So basically, your f of xy ds will change to f of rt norm r prime t dt. And this, if you remember, this is by Jacobian identity, if you remember it. Some kind of change of variable, and then um, you are, if you remember, we had written x is r cos theta, y is r sin theta. Then dx dy was changed to r dr d theta. This r came because of certain kind of determinant of a Jacobian matrix, if you remember.
We also use this thing while transforming like x and y into a function of u and v.
Yeah, even then only. Even then, you need the determinant of the Jacobian matrix in order to change the this parameter ds dy or dx dy or ds or dr. Anything you want to change, then you want to apply that same thing, and the Jacobian matrix and its determinant is going to help you to do that. So, okay. So once you remember this, then finally our fxy ds over the curve C is nothing but over f of rt, and then norm of r prime t, then dt, and this is over the parameterized curve. Now I will write C prime. Now knowing all this, now can you compute what we want? Yeah. So here is the value. You do that now. Did you receive? I mean, did you find any answer?
Yeah, I'm on the way.
Mm-hmm.
The answer. Okay, just a minute. The answer I got is root 2.
Answer is correct. Answer is root 2. So, okay, let's see how. F of RT. RT is nothing but you have to change x and y to t. That is nothing but 2t. So, x plus y ds over the curve is nothing but 2t, but ds is nothing but it's the norm of r. So, RT is nothing but x ti cap plus tj cap, right? And therefore, what will be the r prime t? Star prime t. It's I cap plus j cap, right? So
Yeah,
the norm of this is nothing but the square root of 1 plus 1, which is root 2. So it is root 2 times dt. But what is the limit of t? It's a 0
0
to
to
1.
1.
Yeah. So therefore, I will simply do this 2 root 2 t dt 0 to 1. And 2 root 2 t square by 2 0 to 1 is nothing but root 2 t square 0 to 1 is root 2. Yeah, so here is the answer. If you, of course, if you forget to write this norm, if you for a moment suppose you forget this, you see your root 2 will be missing then, and you will get only 1.
Yeah,
So make sure when you change the variable you do it appropriately, otherwise you will not get the answer. So here is the thing. So what we got is that whenever we have a line integral over a curve with parameterized things, then make sure ds has been written carefully. Fine. Now here is another integral, and again we have to compute it because I want to see something. We will observe the answer, and we have another question based on the similar thing. So we have to compute it. So here is my surface, and I have to find the line integral over the curve C, where its curve C is parameterized by these parameters. Is it a scalar line integral or a vector line integral? This is the first question. Then we'll find the value of integral.
it's a vector line integral.
Mm, why? Why? So scalar and vector, we have these notions for what? We defined these notions for, do you remember just in the beginning?
I mean, it affects the output of the function.
Not just that, the line integral itself um, is different, and they're geometrically it's very different. When we have scalar line integral, if you remember, we just saw that it is area above the curve and it, along the curve and below the surface. But the surface is nothing but a, if you remember, it is nothing but this only, x plus y, or let's say any x square plus y square, or any polynomial in xy. So such f are nothing but scalar valued. You see, they are scalar field. Therefore, being this is also defined as a function from R3 to R, it is also scalar field, right? And such integrals we call as scalar line integral. Now, question is, what are vector line integral? Hmm? Suppose I write my f x y z. to be like this: x plus y, square x square plus y, or whatever, such kind of thing, right? Giving a meaning to this is very hard, right?
Yeah.
So such integral, when we have this f, which has been defined in terms of a vector, not a scalar, such integrals are vector line integral, and this is an example of a scalar line integral. Is that okay?
Hmm.
Okay, knowing that it's a scalar line integral and the meaning is it's you have to just find the area. Can you now compute the integral over the curve? So here x is cos t sin t. Okay, so let's see how ds changes. If you remember, it is the norm of under root. I should write x square plus y square plus sorry dx by dt, dy by dt, dz by dt, and then dt. This is nothing but sin square t cos square t plus 1. Mm, yeah, so this is root 2 only, right? This is 1.
Yeah.
So what has been changed now? We have to integrate over x square plus y square plus z time ds over the curve C. Curve C has been given to you that it is parameterized by cos t sin t t, of course. So C is nothing but cos t sin t t, and 0 less than t less than 2 pi. So what would you write here? What are the limits of integral?
0 to 2 pi.
Yeah, and the function?
Function cos square t plus sin square t plus 1 plus t.
Yeah, plus t. So it is 1 plus t, and ds is your root 2 t times dt, right? All right, so what does it give? Root 2 times t plus t square by 2, 0 to 2 pi. What is this finally? Mm,
This is root 2 into 2 pi plus 2 pi square.
yeah, so it's 2 root 2 pi plus pi square. Okay, we'll come back to this. It has certain use. We will see later. So it's a line integral with value this when we parameterize by certain curve. Now here another question. In the previous question, if C is parameterized by another curve, sorry, by the curve which has a parameterization different from what we had earlier. Okay, so I'm parameterizing the same curve, but the parameterization is different now. Then can we compute the same integral and can we compare the answer with the question number 4, and we can we justify why they are same or why they are different, or whatever the answer comes out. Does this question make sense, first of all?
It does.
Okay, so there is a logic behind, and I think we will discuss. So let's solve this. Solution. Okay, so yeah, can we solve it by the same way? What is x? X is hmm?
X is cos 2t,
Yeah,
y sin 2t, z is 2t.
and the limit is this much. And then what is ds? If you remember ds, yeah, isn't it?
Yeah.
Okay. Um. So what is the first derivative? Um, yeah. So what will this be finally?
We get root 8 dt.
Sorry.
Root 8 dt.
Root 8 dt. Okay, let me see how. 4 plus 4 plus 4, right? No, I'm sorry. Yeah, I think this is okay. This is 1. Yeah, you're right. And root 8 is clearly to root 2. Yeah.
Yeah.
Okay, so what we finally got is integral. The function is x square plus y square plus z. So cos square 2t plus sine square 2t plus 2t into dt into root 8. Yeah. And integral is from 0 to pi. So this is nothing but 1. 1 plus 2t. 2 root 2 I will just take out. 2 root 2 is root 8 dt 0 to pi. And what that will be? Sorry. Is that answer same as what we got in the last
It
part?
is.
It is. So the observation is when you parameterize the curve in two different ways, it does not change the area or it does not change the line integral. Yeah, this is the first observation, right?
Yeah.
Question is geometrically how these parameterizations are related. If we see, let's see here, cos t sin t 2t, cos t sin t t. Can you
And in the second case, we have doubled each parameter, but we have halved the limit.
what is the meaning? The difference is the curve has been parameterized so that time runs twice as fast. You see?
Repeat once.
Yeah, so what I'm saying is the only difference is that the curve has been reparameterized so that the, the time runs twice as fast.
Yeah.
Yeah, so when earlier when you were reaching, let's say if I am asking you t equal to pi by 2, hmm?
Mm.
Earlier you were reaching to pi by 2 only. You see here, you are reaching at this part. If I ask you here, suppose this is my, sorry, what I'm saying is this t is my from 0 to 2 pi, let's see. Earlier it is 0 to pi. When I'm here, when I'm reaching this surface, then this is like reaching to the curve. When t is 0, it's okay. When t is 0 pi, then it is 2 pi. It's reaching 2 pi here, but here it is reaching when t is pi, it is reaching pi only. So, the time which is this curve is taking and the curve this is taking, this curve is twice as fast as the previous curve. Yeah, when you reach at the point, let's say x, it will reach 2x there, isn't it?
Yeah.
So the difference geometrically is that you have reparameterized in such a way that you run fast. You run twice as fast what you were running earlier. And therefore, suppose you run fast, then of course the time has been reduced, right? If you are taking 0 to 2 pi, clearly this would have been more because you have covered more area. You have taken longer curve. But since your 0 to 2 pi, make sure that the last point is nothing but 0 to 2 pi. Yeah. This is the last point where you are covering the curve. Here also 0 t is last part is t is 0 to 2 pi only. The difference is that you are slow here and you are fast here.
Mm.
But of course the end points are same. You are going from one part to another part. Just that you are moving fast. I hope this clears some geometric meaning. Is that okay?
Yeah.
Okay, so therefore, even if you are running fast, as much as area you want to cover here, that will be same there. Therefore, the answer will not change. Yeah. Okay. Here is another good question I feel. Suppose a wire has a shape and that can be modeled with a parametrization. I don't know how the wire looks like, but I have parameterized that wire as in such a way that it has certain coordinates. And this is bounded by 0 to 4 pi. Now I want to find the length of the wire. Just think for some time. Think if that you can do it.
Yeah, we can.
Yeah, how?
Like in general, the
Mm-hmm.
length can be defined as the integral of some dx.
Exactly right. Exactly right. Now, since you know the idea, can you use that idea here? I think you are very close, and um, just think
We
about
will not have the functional part because there is no area. There's just the length.
exactly, exactly, exactly. So I think you got what I want to somehow say to you that okay. So if you have, let's say, just you have A to B. I'm going to find the length of this segment, line segment, let's say. What is that? Just by looking at, I know what is the difference, yeah? What is the length? It is the b minus a, right?
B minus A.
If I just write this way, this is important. What does it give?
B minus A.
B minus a. That's all. So, and if I just change it to, what does it give?
It will give the area between
Area of
the
the
limits
region R.
in the rectangular
Uh,
domain.
Yeah, area of the region R. Whatever R, I don't know what R is. If I ask you here dx, dy, dz, and if I ask you here some W, what is this?
Volume.
Volume of W. That's all. So if once we know this all part, then we should be able to know the length of the wire. The coordinates are given to us. Yeah. So what is that? Now since what we know is the length of the curve is, if you have F, you know you want area. If you do not have F, then this is nothing but the length of the curve, isn't it?
Yeah.
Okay, since you know this, now can you compute what is this length? Do not forget to change ds to dt, curve to t, and then integrate.
And the final integral would be
Yeah.
root of 1 plus t dt from 0
Okay.
to 4 pi.
Mm-hmm. So 1 dot ds over c, if we call this is nothing but dx by dt square dy. This cannot be forgotten. You need to uh, write this all the time that ds is nothing but this time dot dt. And of course, you have to parameterize over the parameter t, which is 0 to 4 pi. So this is 0 to 4 pi. What is the derivative? Uh, minus sin t whole square cos t whole square and 3 by 2 1 by 2. So it is just t 1 by 2, right? Is that you are getting?
Yeah.
So this will be 1 plus t, then root, then dt, then 4 pi. Now how to integrate this? If you have any function, of course I cannot write this because any function I need to say what that function is, unless I say that I cannot integrate it. Yeah, what is the integration of this? Okay, if not, then you can tell this maybe. That will help.
Just
If you can tell this, you should be able to tell this.
if we use a standard rule, this becomes 1 plus t to the power 3 by 2 into 2 by
Mhm.
3.
Exactly right. You have to just go by this. That's all. 0 to 4 pi. It's the same thing.
And okay, I have this question. Like while
Mm-hmm.
we differentiate,
Mm-hmm.
when we go by the power rule,
Mm-hmm.
after that we use the chain rule. We get inside it, what we
Mm-hmm.
get, we multiply.
Yeah.
And for integration, we just divide what we get after getting inside the chain. Is
Yeah.
that the rule or is it more
Yeah.
complicated?
No, 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 no. That's all. That's all. Suppose I
Okay.
ask you, what do I say? T square. Oh, no, no, no. Square do not have certain good thing. Sine t square. How do you integrate this? No, I think before that you have to change something. It's not that simple.
Okay,
Integration
like
is
if
not
we
okay.
integrate, normally if we integrate, suppose 1 by 1 minus 2x,
Mm-hmm.
then first we get log of 1 minus 2x and
Is
we
it
divide it
this?
by minus 2.
Yeah, exactly. You have to take log of 1 minus 2x and whatever is inside you have to divide by that. Yeah.
Okay.
Yeah, I mean, you have to follow the same rule. There is nothing different. Yeah. So it's the same thing. You have this power half. So you just add up one power and divide by the same power. So you get this. Yeah, it's the same rule.
Yeah.
2 by 3 and then 1 plus 4 pi power 3 by 2 and then
Okay, ma'am, just
minus.
hold on a minute, just a minute.
Sure.
Yeah, ma'am, I'm back.
Okay. Yeah. So here we just put the limits 1 plus 4 pi power 3 by 2. And of course, if I put t to be 0, it will be just 1. So here we'll not simplify, we'll remain with this. And then this is the final answer. So this we got the length of the wire. So, if somebody asks this question, just by looking at the question, it doesn't seem any information. Yeah, how would we compute it? But a slight observation that length can be computed by integral, that would tell you everything. So yeah, so once we know the basic behind it, I think it's very simple to do. But of course, one should know the basics. Yeah. Okay. Now here is another question. Suppose we have a function. Look at f carefully. Then what is this meaning?
This would be a vector valued or a vector field.
Exactly. One observation is this is not scalar valued, it is vector valued. So it's a vector field, and therefore the integral is a vector field integral. What do we say? I just forgot the name. What was that? Vector line integral. Yeah, it's a vector line integral. Of course, it cannot be the meaning. It cannot be same that we had for scalar valued integral, scalar line integral. So something else is here. Okay, if I ask you a random question, suppose you are pushing a wall, hmm? And of course you will not be able to move the wall, right? But you're pushing, you are putting force on it, but it's not moving. Will you call that be a work? So you are pushing so let's say in the morning till the morning till the evening, you are pushing from morning till evening. The wall is of course not, it did not move at all. Do you call that whatever you did is a work done by you?
In physics, no,
And why that?
because the displacement of the wall is zero.
Exactly. So, some force you are putting, and force has a magnitude as well as direction. Yeah, it's a vector, right? Force is a vector. And you're making certain kind of displacement. And then force time displacement is exactly your work done. Can you relate now with this, what we are writing, with what I told?
Ma'am, repeat the last part, which what you told.
Yeah, I'm just saying that suppose you have this force which has magnitude direction, you have certain direction where if you are putting a force, and there is a displacement which you have certain displacement in that direction wherever you are moving it, then the force time displacement will give you the work done. Of course, if there is no displacement, there is no work, even if you have put force on it. So the force time displacement, where certain displacement is okay, where certain force is with having magnitude as well as direction. I am whatever I'm repeating, there are certain words which I am focusing on. First word is force having magnitude as well as direction. And there is a displacement, certain dx or ds or d, whatever dr. Hmm?
Yeah.
Okay, can you relate that thing which we discussed, just certain kind of work done? With this, what we are writing here is a vector line integral.
Yeah.
So now, if I ask you, what is this geometric meaning? Along certain direction, you are putting a force F having certain displacement dr. Now,
Okay, like work is the total force into the
mhm,
total displacement which we have.
yes,
So FDR can be interpreted as amount of force that is required to cause a very small displacement in the object considered here.
yes, yes, but along which path? That is also crucial, right?
Yeah, along the path of the displacement.
Well, if I ask you, the work done supposed by vector field depends on which of course it depends on the direction in which particle is moving. Yeah, and of course wherever it's moving, it should have certain path which has followed. So there should be a curve which it has been following in order to make a displacement, and of course certain force is independent of what curve you are making, but the displacement is of course it depends on which curve you are following. So this work done is the work done by the particle in the direction along the curve C. Does that make sense here? So the particle is moving along this curve C, and then there is a certain displacement. Yeah,
Yeah, like
I
when we are going along a curve,
yeah.
at each instance, the direction of the displacement will be different. So we are
Yes,
considering each direction at an instant and
yes,
integrating that.
yes, yes, exactly. So there is no one path which there is no one direction which we am saying that its displacement is, suppose I'm just giving you uh, pushing a table. You can push the table in any direction, right? So the displacement, of course, will happen based on what curve you are following, and of course, it will depend each instant. So therefore, this is nothing but the whole geometric meaning of F dot dr over C is nothing but the work done by the particle with the force F along the curve C, along the path C, or along the direction C, I should say. I mean, the direction has to be followed along that curve. You cannot go beyond the curve, right? Does it make sense?
Yeah,
All right. So the meaning, first, which we were discussing is something else, which was scalar field. The meaning which now we are discussing is something quite different. Is nothing but the work done. Yeah. All right. So now, since you understood the meaning, so let's see certain examples. Mm, so it is nothing but the geometrically. Let me write. It means the work done by Vector field you can say by the particle you say, I mean, I just say by the vector field F um, along the direction or in the direction maybe, the direction along curve C. Alright, so both the things have very different meaning as we just saw. Alright, suppose we know now the geometric meaning. We need to compute also. Earlier, what we were computing has certain different meaning. Here, it has certain different meaning. Here, can you tell me how to compute this f dot dr? Of course, the dr is very specifically given to you. It's this little bit displacement in x direction, little bit displacement in y direction, little bit displacement in the z direction.
Here we will not take the norm because
Of
there is
course,
no
yeah.
particular magnitude in that way.
And focus, it's a dot product. Yeah, if you have a dot product, when you have f, it has certain component in x direction, certain component in y direction, because it's a vector valued, right? So you do not have a scalar now, you have a vector now, and you have another vector. Dot product has itself its meaning. So what does it finally give? Can you write that? I think you can.
Like in case of a scalar field, we are multiplying a scalar with another scalar and then we are
Mm-hmm.
integrating.
Mm-hmm.
And f dot dr gives the, like, here we deal with the component of f in the direction of r at an
Mm-hmm.
instant.
Mm-hmm.
And so eventually we will get the total magnitude by calculating the dot product at each instance.
Yeah, so what do we do here is this. We have f dot dr and along of course certain curve C, then of course you know that dr is nothing but dx dy. I should not write this dx dy dz. Therefore, if I ask you what is dr by dt times dt, isn't it just dr, right? This is same as
Yeah.
dr. Yeah. So what do I do? Now can you tell me what is f dot dr? I think you should be able to write. When I parameterize it, okay, after parameterizing. Suppose C is parameterized by xt, yt, zt. And T has certain region T1, T, T2. Now can you tell me? I think you can. Yeah, integral will be from,
Yeah, from T1 to T2.
yeah, from T1 to T2. Earlier f is f of x comma y comma z. Now it will be t y z t, isn't it?
Yeah.
Now dot product with dr, but you want to change everything to dt, but you know dr is same as something, and therefore you can write. Now can you tell what is that? It's a dot product with, hmm?
The determinant of the Jacobian.
Well, carefully, if you look in this case, we don't have to go by that. We have anyway written everything. Focus
Yeah.
here.
Okay, we already have written dx dt dy dt dz dt.
Now, can you tell me what is this finally? Like you have f, suppose this component is f1 I cap, f2 j cap, f3 k cap. Now can you tell?
Like the second component can just be written as r dash t.
Yes, exactly. So isn't it is just this f1 times dx by dt, f2 times dy by dt, f3 times dz by dt. Yeah. So
Yeah,
this is quite simpler than what we had earlier. Remember, I'll just recall the other fact. Here the meaning it would become just f1 times dx by dt, f2 times dy by dt, and f3 times dz by dt, and then whole integral into dt over the limits. Earlier it was f times, since f was a scalar, you cannot multiply this with a vector. Therefore, earlier r prime t you have to take the norm, then dt, and then from t1 to t3. You see the difference?
yeah.
Okay, so I think you've understood it. Then let's compute certain things. Here we have to find the integral of this f dot dr over the curve. See, remember f is a vector valued function. Okay, so are you doing it?
Yeah, I'm doing it.
Okay.
Okay, I'm just stuck at one portion.
Mm-hmm.
Like in this one, how do we transform minus y and x into functions of t?
Oh, is that so? You're stuck. R is, remember, R is x I cap. Mm, usually R
Okay,
is
okay,
x I
got
cap.
it, got it.
Okay.
Final answer is 0.
0 is it? Let me see. It should not be 0. I think you recheck once. Okay, let's do it together then. You can see it. Yeah, so for far t, if you remember, times r prime t, again vector, both vectors dot product makes sense, dt over the curve 0 pi. All right. So yeah, the function is y comma minus y comma x, and that would mean that you are writing minus sine t I cap plus x is cos t j cap. Yeah, r prime t is minus sine t I cap plus cos t j cap, isn't it? Times dt, and you have to integrate 0 to pi. Is that okay?
Yeah.
So this, what is this finally?
Just a minute. I think I did make a mistake here. Yeah.
Mm-hmm. It's okay. So
Yeah,
what did you get?
it would be sine square t plus cos square t.
Yeah, and therefore it would be sine square t plus cos square t dt, and then 0 to pi. And this is nothing but 1 dt 0 to pi. So answer is
Pi. I think ma'am is disconnected temporarily. Hello NPTEL. Hello viewers.
hello.
And now you're audible.
Okay, so let's continue. Yeah, all right. So we did this part, that this value of the integral is this. Now, suppose, okay, now I want to observe something. We want to observe, let's say, something here, and we want to compute the same integral, same f what we had now in this question. But I want to parameterize this curve by another curve. Sorry, another parameterization, not another curve, another parameterization. Here I want you to check something. Of course, we will see what the geometric difference between these two things. But let's compute first. So f is the same, so let me write what is f. F we had is minus y comma x. So fxy is minus yi cap plus xj cap. And sorry. And we have r here in this case is cos t plus pi. Remember, this is again vector value, cos t plus pi I cap sin t j cap. So therefore, here xt is cos t plus pi and yt is sin t. Limits are of course 0 to t to pi. Alright, so with this, can you quickly compute what this f dot dr is?
Yeah. Is it minus pi?
It is minus pi. Okay, let me just compute and then we'll discuss why what is happening here. F dot dr over the curve is 0 to pi. My f is nothing but minus sine t I cap plus cos t plus pi j cap. And then the dot product is with um, r prime t, which is minus sine t plus pi I cap plus cos t j cap, isn't it?
Yeah.
Times dt. So 0 to pi, mm, what that would be? What is sine p, pi plus t? Pi plus anything? It's minus sine t, right? So I can write this as minus sine t. Sorry, plus sine t. Because sine of pi plus something is minus of that and therefore it becomes plus. Alright, and what is cos pi plus t? I think it is minus cos t. So finally this is minus sine t I cap minus cos t j cap, and this is sine t I cap plus cos t j cap. Yeah. If I just multiply, they take the dot product. This is nothing but minus sine square t plus cos square t. And then there is a dt, and this is all. So minus dt 0 to pi, as you said, this is minus pi. Now, uh, work
Okay,
done.
ma'am, could you just tell me how you did that part?
Sorry, what is it?
Transforming pi plus t to t. I have forgotten the way.
Oh, okay, okay. So, if you remember, the first two quadrant, sign will not change. Uh, if you have sine of pi plus, sorry, pi minus something, then it is just sine of that number only, whatever you have here. If you have sine of pi plus something, after crossing pi, you will get a minus sign, of course, but sign will remain sign. But if you have sine pi by 2 plus something, the sign will not change. Sign meaning there are two different. Sign is a function, sign is 1 plus minus sign. So the function will change to cos, but there is a positive sign here. But whatever there is, it will remain that. As soon as you have pi, the function will remain same. There is a sign over there. Is it a plus? Is it minus? It depends. So my case is this case. So once you cross pi, and the function is sign, then it will just be remain sign, but the signature will be minus one here. Same thing with the
Okay, I think
cos.
there was something like this. In the first quadrant, all of the functions are positive.
Yes,
In the
fourth
second
quadrant.
one, sine and cosec are positive.
Yeah,
In the third one, cosine and sec are positive. In the fourth, tan and cot are positive.
yeah. I
Based
mean,
on
I
this, we are
don't
doing.
remember all. Yeah, yeah. That's I am just using some kind of trigonometric things. I am not doing hard maths here. Okay. Um, oh, you were doing by this way. Cos A, cos B minus sin A, sin B. Is that so?
Yeah, like we get
Okay,
cos A,
okay.
cos B plus sin A, sin B. So I
Right,
did
right.
using that one.
Yeah, yeah. I mean, you can do either of the way. Yes. All right. So, yeah, what we were doing is this is nothing but you know, the geometric meaning of the integral is the work done. How this work done comes out to be negative? It's
Yeah,
like
yeah, like the magnitude is the same, the direction is the opposite.
exactly this is what I want to say. Exactly. So, as you pointed out, um, what is the difference then? Huh? How the direction is being different from one case to another case? Let's look it carefully. Let's just see the curve which we are following. As I told you, it is all about which path you are following. Work done can be done, it's okay, but it depends on which kind of path you are following. So let's see the path. I'll just copy both the paths and I will see the difference. Let R1, R2. Okay. Can you tell me what is this curve basically? This curve is not very difficult to draw. We have x coordinate, we have y coordinate. That means we are in the R2 plane. So let me write this as my x, this as my y, and you know x is cos t, y is sin t. If you remember the polar coordinates, I'll just change to polar coordinates. This is my r, if you remember. This is my theta. Hmm?
Yeah.
And let me change by theta by t because we are working over here t instead of theta. Now can you recognize what kind of curve is it? We have x is r cos theta, general kind of thing, and y is r sin theta. Uh,
So
what does
R
it?
equals to 1.
Yeah, first of all, it is r is 1. Another thing is that
And
the
this
equation
can
of,
represent any line depending on the value of t.
well, I should say that if you have x is r cos theta, y is r sin theta, the equation which x and y always satisfies x square plus y square equal to 1, isn't it? Equal to
Yeah,
r
yeah.
square. Depending on r, it's a circle, right? If you see it carefully, it's a circle.
Yeah.
So radius is one, that means it's a unit circle. This is the first information you have. Angle is 0 to pi. So can you tell me till where to where is it circle?
In the upper hemisphere of the circle.
It's a upper half circle, yeah. Half semicircle, I should say. So this is my point 0 at t is pi by 2. Sorry, 0, comma 1. I'm sorry. This is my 1, comma. And this is all in covering. This is my first R1. If I write here, then this is my R1. Can you tell me what is R2? Just see carefully. I think you will be able to say.
Just a minute. Okay, for cos pi plus t is cos t only. So this also represents the same circle.
Minus. Remember minus, minus, minus. As you are crossing pi, it will be minus, right? Is pi minus, it is same. But as soon as it is plus, sign will be minus. Yeah, so here the direction, if I try to rotate, the curve is that you are starting from 0 and you are ending at pi. Yeah, that means you are going this way, you are moving this way. And finally you end up here. So this is not this one, this is I'm sorry. This is the part that the particle has taken in order to move from here to here, and the work has been done starting from here to here. What about the other curve? The starting point is when t is 0. Can you tell me the starting point?
Okay, one more thing. I just verified this one. In the third quadrant, we have tan and cot as positive. In the fourth one, we have cos and sec as positive.
Cos and second positive.
And yeah, with
Yeah,
pi, when we are adding an acute angle, we are ending up in the third quadrant, and cos is negative.
definitely.
That's why we are getting minus cos t in that one.
Right, right. Correct. You are right. Okay, as you know the convention, so there is a negative sign, and therefore now can you tell me? Okay, here the path starts from equal to 0, and the coordinates were cos 0, sin 0. Cos 0 is 1, sin 0 is 0. Therefore, 1 comma 0 is the starting point for the first curve. Move along the curve, move along the curve. The final point is t equal to pi. Cos pi is minus 1, sin pi 0. So we end up at this point. Can you tell me the curve R2T, where it is starting from and where it is ending? I think that will tell you everything.
Like cos phi is minus 1, but minus cos phi will give us plus 1 itself.
Well, yeah, okay, true.
And
So
sin
therefore,
phi gives us 0.
yeah.
So
So at pi, p equal to pi, you got 1 comma 0, isn't it?
so we get the same point.
Yeah, yeah. Point is fine. The point is okay. What about equal to 0, the starting point?
Okay, yeah, we are starting from minus 1 comma 0 and ending at 1 comma 0.
Now, can you tell what is the path?
Yeah, just the opposite of the condition R1 as
Yeah,
parameters.
that's what. This is the whole point here. So the notice that the path is same, but the direction is this. Therefore, if you are moving, directions are different, but you are moving with the same force. Yeah, force is same. You are moving in the same length of the curve, same length of the curve. So how much work has been done? The same as you do in the other direction. But of course, the plus minus sign just tell you the directions where you are moving. That's all. So the difference between the two things is that the work which has been done, that is same. It's just that which direction you are moving, it will be given by the direction of the curve you are moving on. So the whole observation about this was to that C2 is nothing but this curve, the same curve but moving in this direction. And C1 is the same curve but in that direction. Therefore, the two work done are magnitudes are same, but just they are opposite in the direction. All right, that's all. Yeah, this is okay, right?
Yeah.
Question 10. Here we have to find the value of this, where C is the rectangle in a plane with vertices this, and your force or whatever the vector field you say here is given by this formula. So okay, just a comment I want to make here. For I forgot f dot dr along C and f dot dr along minus of C. Can you relate these two? The observation, finally, the conclusion that we made. How these two things are related?
Yeah.
No, how? I'm asking. This is
Yeah.
one
F
part.
f dot dr with limit with the curve minus c would be the negative of f dot dr with curve c.
Exactly. So this is what we finally said. Okay, let's go back. This time your curve has been um, okay. Curve you have to visualize. I am leaving it to you. See carefully. I think it's not that difficult. You just have to see carefully. That's all.
Do we consider r as just x comma y?
Of course, here of course same thing. Yeah, here is nothing but dx I cap plus k. Yeah, I'm doing the same convention. It's the same.
I think your screen is a bit delayed.
Is that so? Okay, let me just try connecting. Okay, I have to connect to different Wi-Fi. If something goes wrong, you have to wait. I think the other one somehow doesn't be working. So I think I will wait until you get what I want to say. Okay, we can go and
Like
I
I
will
can
wait until
see
you
up till
see the
dr
screen.
equals to dxi cap, if that's how much till which you
Okay.
have written.
No. I have written plus dyj cap. So okay, I'm removing certain part. Can you see I'm removing certain thing?
No, it's frozen.
It's not working at all.
It was frozen at
Okay.
dr equals to dxi cap.
Okay, let me just stop sharing and let me start sharing again. I think if that can work. I'm connecting through my mobile data. I'm not very sure that there are not good networks here. So okay, what about now? Can you see?
Yeah, I can hear your voice, but I don't see anything on the screen.
Oh, screen is not at all visible.
No.
Oh my God, what do I do now? I think the Wi-Fi has gone. Okay, allow me for a minute. I think you will. I will be on hold and I will not be connected to this thing maybe for a minute. Let me try that Wi-Fi once.
Okay.
Just
Hello, NPTEL. Always an exciting experience to study with Ankita ma'am. I think she will be a great professor after her PhD. Let's hope for the best.
now and I have joined again. I am
I can hear your voice.
um, for you because you were in the meeting. Still going on. Um, can you see that there was recording when you were there in the meeting?
Yeah, the recording was on while I was there, like the red dot on the
Okay,
top
I
left.
hope that all the time.
Yeah, it was there throughout.
Okay, I hope that I don't have to repeat this session again. That will be painful. Okay, let me just share my screen. I hope it will work because here, the Wi-Fi is really. Can you see my screen now?
Yeah, I
It
can
will
see
come, I
only
guess. It will come.
white.
Wait for some time. It will. Nothing on the screen.
It's just a white blank screen.
Oh, okay, just give me a moment. Okay, what about now?
Yeah, I still see a blank screen. Maybe I am trying to rejoin once. If that fixes it.
Hello. Are you saying something? Hello?
Hello.
I think you got disconnected, right?
I tried to rejoin to see if that fixes the thing.
Oh my god, then there was no recording, right? Nobody was there in the meeting.
Uh, like now it is, did you restart the recording? Because it still shows
I
recording now.
Okay, no, I did not do anything. Okay, let's hope that I don't have to
That
record
that
this.
means it's still there. It was going on.
Okay, maybe there is nobody in the session and still the recording was there. Okay, I hope that this is the case. Otherwise, I have to record the whole session again without anybody. Okay, let's just continue. I'm sorry for such a mess. This Wi-Fi is so bad here. I think you can see now. Hello?
I only see your icon.
I can even now.
Like it does not show that you are shading anything at all.
Okay, let me try once again. Now?
Still not.
Okay, let's wait for a minute. I do not have here the mobile, even mobile networks are so poor here that I cannot use my mobile data.
Are you in your hometown right now?
No, actually, I am in Chennai now.
Okay.
I am at IMSC. So this IMSC has this Wi-Fi issue right now. Okay, what about is it visible now?
Not yet.
How would I continue? I'm really not sure. Okay, can we do one thing? I'm not sure how to continue, but I really want to do this question at least. Maybe not the rest of the questions. There was one question on the work done. There was one question on the tangent plane. There was one question on the mass of a spring, and this is one question where I want to find the line integral over the rectangular region. Um okay, let's do at least this one, and I'll then try to do the remaining things in the next session. Okay, so what I want to say here, find the value of integral. You write maybe in your notebook. Find integral f dot dr over the curve C. C is the rectangle in the plane with the vertices. First vertex 0, 0. Second one 2, 0. Third one 2, comma 1. Fourth one 0, comma 1. And what is the force or whatever f you call? It is x minus 2y I cap plus y minus x j cap. Yeah, it's a
Okay.
function of x and y. Okay. Now, can you try looking at the curve? Because it's all the time looking the curve very specifically and then try to see how to interpret the curve. You are all the time we are parameterizing the curve and then we are finding this. So try to see rectangle and if you can parameterize it.
Yeah, I have drawn the rectangle.
You have drawn the rectangle, good. So, okay, let me also draw. I don't know whether you can see or not, but I'll also draw here. So first coordinate is 0, 0, starts from the origin, goes to 2, 0, so it's a 2 unit on the x-axis, 2, 0. Yeah, so x-axis we have till 2, comma 0, this rectangle. Then we have 2 comma 1, so it's a 1 unit to the y-axis, so 2 comma 1. And then 0 comma 1, it will just touches the y-axis at 0 comma 1. Yeah, I think
Yeah,
I'm repeating everything what I'm drawing, so I think you'll be able to follow. Now for each line, yeah, you since your curve is nothing but it's a four curves actually. C1 is the x-axis curve, C2 is the parallel to the y-axis curve, C3 is the parallel to the x-axis curve, and C4 is the line on the y-axis. Yeah.
yeah.
Then can you write the equation for C1, for C2, for C3, and C4? And can you then help? Can you use those equations to integrate the function?
Okay, like C1 is y equal to 0,
Y equal to 0 and
C2 is x equal to 2, C3 is y equal to 1,
Mhm.
C4 is x equal to 0.
Exactly right. But you just have told me those which are uniform, but something is varying also, right? If I ask you on C1, something is varying, right?
I didn't get this part which you said, something is varying.
Okay, I just said that your C1 curve is nothing but the tuples, right? It is just not the one thing. You just told me y equal to 0. It's okay. But your x is also from 0 to 2.
Yeah,
So you'll just parameterize your C1 curve by t comma 0, where t varies from 0 to 2. Then the other curve C2 you'll parameterize by 2 comma t, where t varies from 0 to 1.
okay.
The third curve will be parameterized from, yeah, here it is important. Where you are moving to where? You are moving from 2 comma 1 to 0 comma 1. So how would you write the equation for the x coordinate? Y is
Okay,
okay, y is 1.
just a minute.
Mm-hmm.
So like C2 can be represented as uh just a
2
minute.
comma t, t
2
from 0
comma
to
t.
1.
So C would be now t comma 1,
Mm-hmm.
and t is varying from again 0 to 2.
0 to 2 it's for C1, right?
Yeah.
Right.
No, also for C3.
Well, it depends on the direction. That's what I'm saying. You know,
Yeah.
you are moving. Hmm.
Okay, got it. So it will from 2 to 0, and for
Yeah.
C4 that would be 0 comma t, and t varies from 1 to 0.
Yeah. So what would I write? Let me just tell you. I would write this way. I will write C3 to be 2 minus T to 1, and T varies from 0 to 2. What you are saying is also correct. There is no issue. But I'll write this way. I'll write T 2 minus T, and T start from 0, goes to 2. So 2
Okay.
minus T, if I take T to be 0, it will 2. It will give me 2. If I take 2 minus T and T equal to 2, it will give me 0. So it will go from 2 to 0. The path is 2 minus T. T varies from 0 to 2.
Hmm.
The same thing you'll write for the last one. You'll write 0 comma 1 minus T. T varies from 0 to 1. Isn't it?
Yeah.
Okay, since you followed this, I will write now f dot dr by sum of these four curves. I have now four curves. You see,
Yeah.
can you do that integration?
Yeah, I'll try to do it.
Mm-hmm. I think I'll stop with this because it's too hard for to tell all the details without even showing what is happening. So you just compute and I will just discuss the solution and then we'll end up. Okay, so let me just try to say something what I'm doing and then over the curve C1, let's say. So what we want to compute is f at that r of t. Hmm. For us, r of t is nothing but x of t plus y of t. For the first curve, my x of t is nothing but it's t and limits of t is 0 to 2. Yeah.
Yeah.
And y of t is entirely 0. So my f of x of t would become xi cap minus xj cap. That means ti cap minus tj cap. Yeah.
Yeah.
Dot x prime t is nothing but only t. So if I take the derivative, it will be just I cap. Hmm? Yt is
Yes.
already 0, so there is no derivative. So I'll just take 0 j cap.
The final answer I got is 3.
3. Just a moment. Oh, it is 2 actually. Maybe there are certain things because there are many curves, Might have done certain mistake. I'll just say, okay, from the first curve, I will tell you what is the answer. It is just t times dt 0 to 2.
Yeah.
Are you- Yeah, so it will
Yeah.
give you 1. Sorry. It will
It
give
will
you
give
2.
us 2.
2, right. 4 by 2, this is 2. Yeah. The second curve, when I say over C2, the second curve has entirely x to be 2 and y is t and t varies from 0 to 1. So the integral would be 0 to 1 t minus 2 dt. Is that okay?
Yes.
That would be t square by 2 minus t 2t 0 to 1 and this will give you minus 3 by 2.
Yes.
Okay, so final two answers are fine. But the third answer, over the curve C3, f dot dr would be only t dt. I think you might have changed these things with your own things. Okay, for me here xt is 2 minus t. Are you following the same xt? 2 minus t.
Uh,
No, you are taking t from 2 to 0. Is that so?
no, I did try to transform, but I mixed up things, yeah, between the normal
Oh,
form and the transform form. Yeah.
okay. Maybe you can write and you can do yourself. If you take xt to be 2 minus t, and t varies from 0 to 2, and in that case your y is, I guess, 1, then it would give the integral over this C3 curve, it would be 2 only, just 2. You can check it. When I take the fourth curve parameterized in the way x is entirely 0 and yt is 1 minus t, t varies from 0 to 1, the integral would be over C4 would be minus of 1 by 2. So f dot dr would be minus 1 by 2. So when I add up, it will be 2 from the first one, minus 3 by 2 from the second one, 2 again from the third one, and minus 1 by 2 from the last one. And what would I get is 4 minus 2, which is just 2. I think this you can do. I think you got the idea how to split up your
Yeah.
curve.
Yeah.
Yeah, and split the curve in such a way that it can be written as union of 4 curves and parameterize your function, your curve by each such curve and then sum up all the area, not area, the work done on each curve.
Yeah.
All right, so I think I'll just, I don't know how to say it, but um, I had 4 more questions and I could not do it. I'm really sorry for the Wi-Fi issue. You are not able to see even now.
No.
Okay, just a moment. I'll try once more if that can work. Otherwise, I will just stop here. I have
It
stopped.
was a different kind of experience to do math like this.
Yeah, I don't know. It's very bad. It's like an adventure for you today. Can you see it now?
No.
I can't do. I mean, I really cannot help you. Um, I'm literally very sorry. Okay, I mean, I cannot do anything, and I think it's good to stop
We
and
have
like.
also faced these things during the lockdown while
Mm,
presenting things to the teacher, and the Wi-Fi
mm.
was malfunctioning.
And then what happened in the end?
Yeah, we would use different approaches. Like sometimes
Like
we
a.
would have to reschedule.
Mm-hmm,
Sometimes we would have to join through another mobile or something.
mm-hmm. You know,
Somehow try to do it.
I have this mobile. I'm connected. Okay, let's just stop recording before making any such comments. Okay.